Being a cybersecurity analyst means understanding not only the details about communication software, but also the underlying hardware that makes it happen. In this video, we'll talk about network hardware. Network hardware begins with cables, such as copper wires. Now, copper wire cabling is used to transmit electronic signals down the copper wires. Commonly, we'll see unshielded twisted pair, or UTP, and shielded twisted pair, STP, cables. Shielded twisted pair cables are less susceptible to external interference as signals travel down the copper wires. Copper wires are also susceptible, potentially, to wiretapping, which allows other individuals to capture the signals that are being transmitted. Now, compare that to fiber optic cabling, which transmits pulses of light instead of electricity. This happens over glass or plastic fibers, and it's much more difficult to intercept signals than it would be with wiretapping on copper wire-based cables. The network interface card is another piece of hardware that exists in communicating devices. It's called a layer 2 device. It might be a wired NIC. So for example, server hardware physically might have 3 or 4 NICs, or we might have a Wi-Fi NIC built into a laptop or a smartphone. Same goes for Bluetooth. Either way, if it receives and transmits on a network, it's a network interface card. Network interface cards have a hardware or MAC address, which is called a layer 2 address. Now, this is the 48-bit hexadecimal unique identifier for a network interface on the local area network only. The MAC address can also be spoofed, so a malicious user could use freely available software to make their device look like some other valid device that is a trusted MAC address. NICs also support multi-homing in a device where there's more than one NIC, and we'll often see this in firewall devices. NIC teaming allows us to put multiple network cards working together for the purposes of either load balancing or aggregated bandwidth. The other way we can look at this is even a single network interface card could have multiple IP addresses, and you might find that happening if you've got, for instance, a web server hosting multiple different websites, each on a different IP address. So each network interface card can also have different network traffic rules applied that controls what traffic is allowed in through that card or out through the card, and that's especially relevant in multi-homing firewall devices. Routers have at least 2 NICs, if not more, so they can take traffic in from one interface and route it to a network through a different interface. Layer 2 and Layer 3 switches supersede hubs. They are the central connectivity point in a star-wired network, and they're very common. Managed switches are managed usually over secure protocols such as HTTPS or SSH, as opposed to HTTP or Telnet, which are not considered secure for transmission of credentials. A managed switch is called managed because you can remotely manage it and configure and tweak how the ports behave and so on. Lower end or cheaper switches will still function as a central connectivity point, but you can't really configure them in any way because they wouldn't be managed. We can also configure a monitoring port on a switch so that we can capture network traffic. Now, the nature of a switch is that any traffic sent between 2 nodes is only seen by those nodes and not every other port in the switch. So if we want to capture all network traffic in a switch, we usually put our device into, let's say, port 1 of a switch, configure port monitoring for all the other ports so that it copies all the packets to port 1, where we're running our packet capturing tool or software. Within a switch, we can configure a VLAN, a virtual local area network. This allows for network traffic segmentation. It also allows us to do this for the purposes of performance. Having smaller networks as opposed to one big one is much more efficient. Also for security, we might, for instance, want storage area network traffic in the form of iSCSI to occur on a separate VLAN from regular user traffic. All ports on a switch are in a single VLAN by default, but of course, this can be changed on a managed switch. VLAN membership can be determined by the physical port that a cable is plugged into on the switch, or it could even be the IP address of the plug-in device, and so on. A router is a layer 3 device, and it's a crucial part of network hardware that sends traffic from one network to another. Without routers, the internet could not exist. Routers have at least 2 network interfaces. They do not forward network broadcasts, and the reason for this is due to security and performance. Routers can be configured with packet filtering rules. In this way, they're considered a layer 4 type of firewall because they can block up to and including the port address for a network service. Of course, they can also allow or deny traffic based on IP address and things like that. Routers need to be configured with the correct IP addressing in order to route traffic correctly. Network devices point to the router interface on their subnet as the default gateway, and that's how a device on a network can communicate outside of the local area network. Routers maintain their own routing tables in memory. So routers have memory just like a regular PC, and a routing table lists the best way to transmit packets to a remote network. So the routing table contains things like network addresses. There could be multiple routes to the same location, but with different efficiencies. We can also allocate, or it might automatically be determined, the routing cost. The routing cost is used to determine which path we should take when we have multiple paths to the same destination. Routers also share routing information with other routers using routing protocols such as RIP, the Routing Information Protocol, OSPF, Open Shortest Path First, and BGP, the Border Gateway Protocol. Routers are ideally managed over the network by administrators via HTTPS or SSH as opposed to the insecure counterparts of HTTP or Telnet. In our diagram, we see two routers, router 0 and router 1. Now, if we take a look at our diagram in the upper left, we've got host 0, and in the bottom left, we've got host 1. Now, in order for those devices to send traffic through router 0, if they're on the same local area network, they need to point to the network interface for router 0 on their local subnet. Now, router 0 would then be connected in some way to router 1, and sometimes the connection between routers is called a backbone. So then the traffic could be routed to router 1. Now, in the same way, in our diagram, the devices over on the right, hosts 2 and 3, would have to point to the IP address of the network interface for router 1 on their local area network. So the theme here is that you can't point to a router interface that's not on your local area network, because how would you get to it in the first place? Because that's the purpose of the router, or as it's called in IP networks, the default gateway. Wireless access points and routers are considered layer 2 and 3 devices. This is because they deal with not only IP addresses, layer 3 addresses, but also MAC addresses, layer 2. Wireless access points and routers allow wireless connectivity for Wi-Fi networking, Bluetooth, and they also create a wireless local area network, or a WLAN. They often have a wired connection to network infrastructure, and they're ideally managed like network equipment should be over a secure protocol such as HTTPS or SSH. Other network equipment that we might encounter include appliances of various types, like hardware encryption and decryption devices, voice over IP and telephony integration devices, which should be placed on a separate VLAN for performance and security reasons. We might also have hardware firewalls, hardware VPNs, and also different types of computing appliances in manufacturing and industrial environments. In this video, we discussed network hardware.